Welcome back, guys. We are doing theorem proving with our proof assistant tool Lean. We're learning the tool, so we're doing tutorials and exercises. We're using the source book Mathematics in Lean, and we're on chapter 5, number theory. This is teaching us different aspects of MathLib, a giant library for expressing mathematics. And we are going to prove a fun theorem that there are infinitely many primes. There are infinitely many prime numbers. And so we're going to have to use some of the tools we just learned, induction and recursion. Now, we're very familiar with these tools from theorem proving in Lean and just things like natural numbers game. But one way to prove this, so here's the way that the proof approach we're going to take here, is to say that for every natural number n, there's a prime number greater than n. And the way we'll prove that is to say that any prime factor of n factorial plus 1 has to be at least n. First we're going to have to show that any number greater than or equal to 2 has a prime factor. And then to show that, we'll need to show that any natural number that's not equal to 0 or 1 is greater than or equal to 2. And so, this is a point that I've noticed. You know, there's a lot of details when you're reading a real proof. There's sort of trivial cases that you just sort of ignore and gloss over, and you're just like, oh yeah, don't have to worry about that. But with the formalization, with the theorem proof checker, you need to provide little certificates that all these little edge cases are satisfied. They can be kind of annoying to prove, like in terms of the amount of time you spend. But Lean tries to have a lot of facilities to make this sort of thing easier. All right, so here is our first theorem. If m is a natural number not equal to 0 or 1, then it's at least 2. Okay, so first, so we're going to consider the cases. And in our first case, the conclusion is not true. 0 is not less than or equal to 2 is not less than or equal to 0. But also we have this contradictory hypothesis, so we're saved. So this case is impossible because it contradicts our hypothesis. So this is the case where n equals 0. We started here where m is arbitrary, and then we're going to do cases of m. So the first case is that m is 0, but that's not allowed. So now we're in the case where m is the successor of something. So we're sort of working inductively, and we're going to consider again where m is 0 or the successor. So this plugs in 0 for m, and we're dealing with m successor, so basically we're dealing with the case 1. And again, the conclusion is false. 2 is not less than or equal to 1, but also the premise is false, so we're saved. Right, so now this is the real case. The real case is to show that if a number is a successor of a successor, then it's at least 2. And so we did something like this in the proof, in the other, some proofs we did related to, I did these offline, related to induction and recursion. We did some proofs had this form that were sort of like successor less than or equal to successor. Here we had a couple of them in a row because we're dealing with basically 2. This is a neat trick. So I counted out the number of times I needed to do it, but repeat will just do it until it doesn't work anymore. So this is sort of the injectivity of the successor function. If successor of A equals successor B, then A equals B, and so we can sort of work backwards. And it knows that 2 is successor of 0, and M is successor. This is successor of M. So we're going to use injectivity to sort of pull off the successors, and we're left with 0 is greater than or equal to M, and this is just a basic theorem of natural numbers, that they're at least as big as 0. All right, so kind of a trivial theorem, but actually a little involved to prove from first principles using the inductive properties of natural numbers. Okay. I guess this is a different proof. Using interval cases automatically splits the goal into cases when a variable is contained in an interval of natural numbers or integers. All right. Interval cases searches for upper and lower bounds on a variable n, and if bounds are found, it splits into separate cases for each possible value of n. Okay, so by contradiction, let's assume that n is not greater than or equal to 2, and which means that m is less than 2, and so we're going to consider cases. Okay, so what are my cases, interval cases? So this interval cases then gives us some cases. It gives us the case, I guess because of h, we know m is less than 2, so it gives us the case 0, it gives us the case 1. Because m is the, so we have that, there's a little magic, but I guess it notices that we have a hypothesis m is less than 2, so it gives us these cases that m is 1 or m is 0. But of course, both of these contradict our hypotheses, so we can apply the contradiction tactic to both of those to close them out. All right. Oh, we have a third technique here. Man, so many proofs that you're at least 2 if you're not equal to 0 or 1. All right, so let's assume that m is not greater than or equal to 2, which means that it's less than 2. All right, and so we have it sort of in this context form where our hypotheses are up above and our conclusions below the turnstile, but we can turn it into this implication using revert. So it's for all m, so we just get these inputs, instead of the inputs being in our context, that m's a natural number, and hypothesis 1, hypothesis 2, hypothesis 3, we string them together in an implication. We have the m, hypothesis 1, hypothesis 2, hypothesis 3 implies false. And then Dec trivial tries to find a decision procedure to solve the problem. Lean knows you can decide the truth value of a statement that begins with a bounded quantifier by deciding each of the finitely many instances. So I guess it's a fancy tactic that Lean will just go through and try them, because we have for all m less than 2. I wonder if Des Trivial needs a concrete bound on M, or if it could be a variable or something. But still finite. Right? Because N could be a variable, not a concrete number, in which case there's a finite but unknown number of cases. I don't know. Let's see what the documentation says. It tries to use decidability to prove a goal. So, yeah. All right, it's good to know that exists. All right, so here now we have the variation dec trivial exclamation point. So this reverts all the hypotheses, and then it tries dec trivial. So basically, this thing that we did here, this revert, it does implicitly. And I guess this works. We don't get it to da, but you know, it's not giving us an error, so I guess that type checks. The statement's a little bit different, though. Guess this is the contrapositive of the one before, which we sort of implicitly do with this contradiction push neg. We're sort of doing the contrapositive. All right. The variant dec trivial exclamation point will revert all the hypotheses. That's what we just read. And then also we can use omega, the omega tactic, the cryptically named omega tactic. All right, attempts to discharge goals in the quantifier-free fragment of linear integer natural number arithmetic using the omega test. Guesses the correct domain by looking at the goals and hypotheses and reverts all relevant hypotheses and variables. Use omega manual to disable automatic reverts and omega int and omega nat to specify the domain. There must be some deep theory here about the omega test, but it seems to do the job as well. So that's cool. Yeah, pretty tricky. All right. So now we have this little trivial theorem that we proved. How many ways did we prove it? 1, 2, 3, 4, 5 different ways we proved this theorem. Now we can get cracking. So we need to show that every natural number greater than or equal to 2 has a prime factor. So let's consider not whether n is prime. So we're gonna consider the case that n is prime, and in this case, well, you know, n divides n. So we can use n. We can use the fact that n is prime, right? So we use n. We use the fact n is prime. We have a certificate for that. And then we just need to know that n divides n, and that's this theorem here. All right. So that case is easy. Now let's assume n is not prime. So n is not prime. Now we need to use strong induction. So strong induction says that if a property is true for every natural number less than this number, we can prove it's true for this number. Whereas for regular induction, we just consider that if it's true for n, then it's true for n plus 1. But here we're sort of assuming that it's true for every number 1 to n. One sec. Okay, so